Substituent effects on PC reductive elimination from Styrylpalladium 2 phosphine complexes, a paper by Wakoika and Ozowa in Organometallics Journal. PC reductive elimination is the main reaction that's studied in this paper, a reaction where PD2 complexes form a new phosphorus-carbon bond. This often gives salts as products. Why is it important in organometallic chemistry and catalysis? Due to the stability/selectivity, uses for PC-containing molecules are widely used in industry. Industry applications include catalysis, where you can modify activity of metal catalysis, enabling efficient chemical transformations. In material science, organophosphorus compounds are used for flame retardants, polymers, and advanced materials. It's also valuable in synthesis of complex organic molecules. And finally, in biochemistry, where enzyme inhibition and signal transduction are some applications. The process regenerates the active metal catalysis, allowing cycles to produce many molecules of desired product. Reactions are also useful in cross-coupling reactions. Here's a summary of what the paper is trying to do. The paper investigates how para-substituents on aromatic groups affect both equilibrium constant and rate constant. Associative and dissociative pathways are also studied. Associative pathways are where the intermediate is a 5-coordinate intermediate before elimination, and dissociative pathways is where the first ligand would have to leave, creating a vacant site before bond formation. This is basically SN1 and SN2 in organic chemistry. The method goes as follows. Styrylpalladium 2 phosphine complexes were used at a dilution of 50 millimolars in deuterated dichloromethane. The solution was brought to 40 degrees Celsius. A phosphorus containing methyl and 2 aromatic groups were added to the reaction mixture in 1:4 equivalents compared to palladium. Proton NMR was used to monitor the PC reductive elimination progress, using tetramethylsilane as a solvent because it's an international standard to calibrate chemical shifts. Pseudo first-order rate constants were estimated using time conversion curves from the starting complexes. The major and minor products are shown below. The minor product was formed by substituent displacement. The reaction rates were measured under conditions where one reaction condition was effectively constant, pseudo first-order conditions, to simplify analysis. Here is palladium on a periodic table. This will help you work out the oxidation state. Palladium 2 complexes convert to product. Palladium shifts to a lower oxidation state, so from 2+ to 0. The pi bond acts as a neutral coordinate ligand with the N2 notation, whilst the alkene molecule is bidentate. You can see this on the left. Here is the reaction mechanism. 2 competing pathways proposed from a 5-complex intermediate are shown below. Metallophosphine intermediates are shown in the green on the right. The second is combined root forming intermediates simultaneously. The 2 molecules are shown below the green. But empirical data supports the metallophosphorine pathway. This pathway is associative. Here is the bonding and spectroscopic evidence. Not all of these use the figure on the right. Palladium 2 complexes contain a trans geometry with 2 phosphines. This is shown by a singlet in the proton decoupled 31 phosphorus NMR. 13 carbon NMR reveals that the palladium carbon bonds are sensitive to styryl substituents. Palladium 0 complexes, shown by PC bond formation and the N2 coordination of styrylphosphonium groups. Large PC coupling with the phosphonium moiety, 77 to 80 Hz, confirms their presence. To conclude this study, the paper discusses how para-substituents on styrylpalladium 2 complexes affect the PC reductive elimination rate. Experimental evidence supports an associated pathway. Substituents effects impact both equilibrium and rate constants. NMR data confirms PC bonds. This improves the understanding of organometallic PC bond reactions. These insights could help in design better catalysis for the use in industrial chemistry.